Oh, good morning. Happy snow day for you. Well, at least for the seniors, it's a happy snow day. The rest of us are not so thrilled with the potential of being in school till the end of June. Okay, so we're going to look at the accumulation function today, which doesn't look any different than any other function you've been working at. And that's okay because we're just going to tie in all the stuff that we already know. So we've got f of x is equal to the integral from -1 to x of f of t dt. Important to definitely note, this is the graph of lowercase f, not uppercase f, which means this right here is your derivative. We've spent a lot of time analyzing functions, so you should already know a bunch of stuff about this derivative function. So about the original function, we already know anything above the x-axis means my original function is increasing. Anytime I'm going below the x-axis, my original function is decreasing. I know 3 happens to be a critical number and a relative max or min because I know we switched directions from increasing to decreasing. And since we went from increasing to decreasing by the first derivative test, I can easily say that x equals 3 happens to be a relative max. So all of this, let's not even forget about this. If we know my derivative graph is increasing, I also know that my function, original function, is concave up. And if my derivative graph is decreasing, I know my original function is concave down. So all of that I know without even looking at any of these particular questions right here. Well, at least we should know. All right, we're going to focus from -1 to 4. We're going to complete the tables for the values of f. Remember, when we integrate, we're finding the actual y values for any given x value. So if the first value is that -1, well, that means you're integrating from -1 to -1 of f of t dt. Now, without even looking at the graph, you know your properties of exponents. That has to be 0. So you already know a particular point on the original function. When x is equal to -1, f of x is equal to 0. So I'm actually going to plot that point. So we're going to repeat that for every single one of these values. So from -1 to 0 of f of t dt. Now I don't have a function, but I do have a graph. And we know that an integral means the area under the curve or the region under the curve. So now I'm looking from -1 to 0. So I look at the graph and I see that I have a familiar geometric shape. At least it should be familiar. You've got yourself a trapezoid. So I want to find the area of that trapezoid. So if I want to find the area of the trapezoid, or you can break it up into a rectangle and a triangle, either one is fine. Area of a trapezoid is 1/2 the height, which is 1, times base 1 and base 2. So we've got 1/2 of 3. So the area of that region is 1.5. And that also means when x is equal to 0, my original function, y, is 1.5. So at 0, we're at 1.5. I'm going to plot that point. You see, we're kind of just plotting the actual original function as we're going through this, using the idea of the area under the curve, again, connecting it back to the fact that that region, that integral, is telling you the actual number. So now, oops, put that right here. Let's go back through the process, -1 to 1, f of t dt. We already know this one's 1.5. So now I'm going to go to this little guy, and I can change colors here. We've got ourselves another trapezoid. So we've got 1/2. Again, the base is 1, or the height is 1. We've got 2 and 3. So that gets me 1/2 of 5. So this trapezoid is 2.5. Now, you might be tempted to say then f of 1 happens to be 2.5. It's not. Remember, this is an accumulation function. So we're looking for the total accumulation from -1 to 1. So we have to add those two together. That means we get 4. So at 1, we're at 4. Notice again, this corresponds to my derivative graph. We know we should be increasing because we're above the x-axis, and we can see that we're concave up. So our graph's going exactly what it should be doing. All right, next, f of 2. So we're going to integrate then from -1 to 2 of f of t dt. Oh, I forgot to jot my answer in here. Hey, look, another trapezoid. No worries. That one again. 1/2. Height is 1. Looks like we're at 3 plus 2.5. And so then that gets me 1/2 of 5.5. That's going to be 2.25. So your value of your integral from -1 to 2 is going to be the sum, the accumulation of all these areas. So we had 4, we're adding another 2.25. So now we're at 6.25. To 6.25. All right, and we keep going. We repeat this process again. So now you're going from 0 to -1 to 3, except our shape changes form. You now have a shape that is just a rectangle. So 1/2 the 1 times the 2.5. So 1/2 of 2.5, that's going to get me 0.75. So my value at 3 is the accumulation of all these. So I'm going to add another 0.75 to my 6.25. So I'm at 7. And then my last value, change it up here with some green. So my integral from -1 to 4. Now I'm below the x-axis, so you know that that means it's negative. Pardon me. So 1/2 my base times my height. But this time it's a negative 0.75. So again, my value of f of 4 is going to be the accumulation of all these values from -1 to 4. So now I'm back to 6.25. I'm going to take my pencil and I'm going to sketch that original curve. Now let's see if it fits all of the properties of everything we already know about a derivative graph. We said that x is equal to 3 was supposed to be our relative max. It is. We go from concave up to concave down. Yes, absolutely. We are increasing all the way until we get to that max, and then we start to decrease. And that's how we use this accumulation function. Okay, so my suggestion is pause the video, try part A and part B of number 2, and then we'll get to part C and part D where we will catch back up with each other. So I'm going to stop this and do a second video.